Good evening and welcome to Gonzaga University. My name is Dr. Brian Henning. I am professor of philosophy and environmental studies and sciences here at Gonzaga University, where I have the pleasure of serving as the director of the Gonzaga Institute for Climate, Water, and the Environment. And as many of you know, this is part of our regular recurring lecture series, the 4-hour Common Home Lecture Series. We host events online and in person. Typically 5 or 6 events a semester. This is our second to last event of this semester. Coming up on December 2nd, we have a fantastic Zoom event. So if you're interested in this event, and I hope you are, don't come here. Or if you are coming here, then bring a computer so you can watch it on Zoom. We're going to be Zooming in a wonderful activist from Rise St. James, from down in Louisiana, who is working in Cancer Alley. And if you know anything about environmental justice in Cancer Alley, this will be one not to miss. And so I hope to see you on December 2nd. Go to gonzaga.edu/climate events. If you have the means to support our work, it is always appreciated. It takes quite a bit to do not only this lecture series, but also the work we do in the community around climate literacy and climate resilience. And so please consider supporting us if you are able. This lecture series we're going to be announcing the spring series right after this next event in December, but I can tell you it's going to have some really exciting features to it. In particular, for example, our keynote for the semester will be Terry Tempest Williams, who's a famous author, will be here in April. That'll be a really exciting event. We're also hosting with the Institute for Informatics and Applied Sciences, Applied Technology, an event on AI, climate change, and energy demand, much on everybody's minds, in addition to some other really great speakers. So look for that announcement about the lecture series coming up in the spring. But without any further ado, I'm really pleased to introduce my colleague, Dr. Kyle Shimabuku, who's a licensed professional engineer and associate professor of civil engineering here at Gonzaga University, where he teaches courses in environmental engineering. His prior research has focused on the removal of contaminants such as PFAS and fluoride from drinking water in both low-income and high-income communities. His current work examines how drinking water utilities can reduce their vulnerability to water quality disruptions following wildfires. As part of his research, he leads several projects focused on treating wildfire-derived carcinogenic contaminants, as well as taste and odor compounds in drinking water sources. He's also investigating post-fire disruption system contamination and the impacts of wildfires on drinking water utility operation costs. Here in the West, obviously, we're experiencing larger, more frequent fires, and so the effect of those on our drinking water is something we should all be concerned about. So please join me in welcoming Dr. Kyle Shimabuku.
All right, thanks for everyone for coming out. A much bigger turnout than I was expecting. So focus of my talk is on the growing megafires, primarily that we're seeing for the first time in the Pacific Northwest. And something I just want to clarify is that the number of fires aren't really increasing in frequency. It's more the megafire are increasing in frequency. And so this figure kind of demonstrates that, averaging out all of the area burned throughout the United States. And so what you can see in the last 10 years is that on average, the area burned has roughly doubled relative to kind of baseline areas burned going back to the 1960s. And the implications of this is pretty significant when you just look at it financially. So just fire suppression costs alone range in the billions of dollars. But some studies that have looked at trying to quantify the true cost of wildfire, so taking into account things like property loss, but then also degradation of ecosystem services, so having a healthy watershed, protected water quality, you're looking at figures that are 30 to maybe 150 times the fire suppression costs alone. What we're particularly concerned with is the degradation of water supplies for drinking water. So for instance, this is a few different postings in the news. One of them from the New York Times just saying that wildfires likely can degrade water quality for maybe 10 years or more. In many of these regions that are experiencing water scarcity, like in the Southwest, if you add on wildfires, it particularly threatens our ability to have sufficient and safe water, since you have this combination of droughts, and then what water does remain is maybe contaminated with large levels of ash from wildfires. Just as one example, there was one community in Las Vegas, New Mexico, a small town there, and they were scrambling around having to kind of rely on water sources that weren't really vetted because their primary water source had been totally destroyed. And so they only had basically 20 days of fresh water and were needing to find an alternative in a pinch. And so these types of challenges are really what concerns water professionals about all of a sudden losing water and then being forced to make trade-offs that you don't want to have to make. Do we use degraded water that's maybe not the safest just to have any water at all? What really kind of keyed the Pacific Northwest water systems, that this is maybe an issue that's not just maybe in the Southwest, it's maybe an issue we need to start thinking about in Oregon and Washington, was the 2020 Labor Day fires. And they were unprecedented in terms of the number of systems that were destroyed. So there were dozens that were directly impacted. There's some photos in the bottom right just showing how these wildfires spread into the urban interface, where they actually destroy drinking water infrastructure, like water storage tanks, pumps, things like that, and pretty much shut down access to water. But there's also nearly 100 water systems whose infrastructure wasn't directly damaged, but their water supplies were compromised to varying degrees. And the way that water supplies get compromised, as you can imagine, after a fire, you basically have what looks like the remains of a campfire spread throughout your watershed. Then during storm events, you might have further or greater levels of erosion because you don't have vegetation to stabilize your slopes in your watershed, and then you get the mobilization of particles. And something I'm particularly concerned with that you're going to be hearing a lot through this presentation is dissolved organic matter. So when those contaminants enter a water treatment plant, they can damage the operations of the water treatment plant, for instance, clog filters, but then also these contaminants can potentially be carcinogenic themselves or maybe interact with disinfectants in our water treatment plant and then form contaminants that can cause health issues, cancer, things like that. Okay, so because most of you probably have not taken a course just strictly on drinking water treatment, I'm going to kind of do my best on simultaneously covering a semester-long class on drinking water treatment and then trying to bring up the issues that wildfires pose to our drinking water systems and then present a little bit of our research on this topic. So first off, I'll give a little bit of a water system overview. And when I say the word water system, it doesn't just mean water treatment system, it also includes the distribution system. So water providers need to manage both treatment and then making sure the water is safe as it travels through our pipe networks and as it's stored in water storage tanks. So arguably the primary objective, and I would say kind of objective 1A at water systems, is to address acute diseases. And that's primarily associated with pathogens, where pathogens are just disease-causing microorganisms. And then I put slash particles and turbidity, and we'll talk more about what that refers to. And then maybe the kind of secondary objective is water systems want to make sure we're not introducing contaminants in our water that cause chronic diseases. So pathogens usually cause those acute, immediate health issues, but then often dissolved contaminants, chemicals, things like PFAS that have been talked about a lot in the news, they don't cause so much acute illness so long as you're not exposed to really high levels. They're more of a concern about causing chronic illness. So they're kind of a 1B in terms of our objectives at a water treatment plant. And then also water systems need to try to provide aesthetically acceptable drinking water so people will trust the water and actually want to drink it. Okay, so let's talk a little bit about why particles are important. So the one reason why we're concerned with just kind of this more broad definition of particles in our water is because pathogens, so what we're looking at on the left there is a Giardia organism that causes diarrheal diseases. It itself is a particle. And so we can think about if we had a water sample that we collected in our water treatment plant that was going to get filtered, we would view that Giardia just like any other particle. And so long as our filter removes particles, we know that some of those particles will be pathogens like Giardia. Measuring Giardia is quite expensive. It's at least $1,000 per sample. Might take several weeks to get the results back. And so because we don't have that kind of time and money to just be constantly measuring the safety of our water, we instead measure things like turbidity. And so what we're looking at here on the left is a turbidity sample that's higher in turbidity. And the way we measure it is we put it in a turbidimeter. Basically what it's measuring is how much light is being scattered or basically reflected. So you have light entering, it hits these particles, that light gets refracted at a 90-degree angle, so it's basically measuring how many particles are reflecting light. And so we might get a turbidity reading of 100 NTU for this sample. And then ideally, what we get coming out of our filter is going to be turbidities less than 0.3. So regulations require that we don't have more than 0.3 NTU 95% of the time passing through our treated drinking water. Okay, so now back to kind of an overview of what conventional water treatment can achieve. So conventional water treatment plants rely on these 5 main processes. So coagulation, flocculation. So that's basically trying to destabilize particles, get them to collide so they'll form larger flocks. And then these larger flocks can more readily settle out of the water and can be more readily filtered. Once we have water with few particles, we then add a disinfectant. Often chlorine is used in maybe about 80–85% of drinking water treatment plants. That's used to then further make sure we're inactivating any pathogens, so we're killing any disease-causing microorganisms. So here in red, I'm showing the regulations in the United States. So again, in the United States, coming out of a filtration process, we need to have our turbidity quite low, less than 0.3 NTU 95% of the time, and less than 1 NTU 100% of the time. And that's not because particles are necessarily bad. We just know if that we're removing particles, we're also removing pathogens, which are also particles. So that's maybe what that water would look like. We then disinfect the water, making sure that we're adding enough disinfectant. For instance, maybe getting 100 milligram per liter times minute value, that's called CT, that we know would get adequate Giardia disinfection. Okay, so water treatment plants like these, they can handle turbidities of about 100 NTU over a sustained period of time. They can handle spikes maybe for a day or two, but beyond about 100 NTU, the processes start to get stressed. Their solids handling capabilities start to get stressed. Water treatment plant operators get stressed out, and no one wants that. So this is kind of what that might look like, 100 NTU. So conventional treatment plants have all 5 of these processes. There's also other water treatment plants that are usually trying to cut out a process, with the most common one being sedimentation. So if you have a sedimentation facility, we would call this a direct, or sorry, if you remove your sedimentation facility, we'd call this a direct filtration plant, right? So this is conventional with sedimentation. This is direct filtration, no sedimentation. The downside of having no sedimentation basin, although it's beneficial in that it can save on capital costs, is that you can only treat turbidities of about 10 NTU. So the water already needs to look pretty clean before you can use this type of water treatment plant. Okay, so why is that significant as it pertains to wildfires? So again, these water treatment plants are designed to remove particles and pathogens, so they should be able to address kind of our first objective at a water facility, and that is to address acute diseases associated with pathogens that are particles. The reason why this is relevant when we think about the effects of wildfires on our water source quality is that we can only handle 10 NTU turbidities if we have direct filtration and up to 100 NTU if we have conventional water treatment plants. So do you think that wildfires could potentially cause turbidity levels to exceed 10 to 100 NTU? So let's get through this brief commercial on YouTube.
The man has jokes.
He's funny. Okay.
Just 5 seconds, bear with me. Skip.
My Uber's 6 minutes away.
Doesn't want to skip.
Can I see you again?
Hi.
Hey.
See you again.
You, yeah.
Yeah, so yeah, sure, yeah, let's try that.
You probably have a few things lying around collecting dust, right? Why not donate them to UGM?
I think this is
I've never.
all right. This is the last time we have to watch
The
a
man has
commercial.
jokes.
He's funny. Okay.
Okay.
Okay. It was just me watching the commercial, fortunately.
At least I muted you.
And just for a little background, this is in the Cache La Poudre River. So this was about we can let it just play from here. So this was in Colorado where they had pretty big fires that impacted their water system. But just kind of as an example of what you might see post-wildfire in a drinking water source.
I've never seen the water quite like this, but it's all right. I mean, it's still cool and good to dip in, you know.
If you get in the river, you can actually feel the soot and ash and debris from the fire just kind of brushing against you. This is usually just, clear. It's beautiful. You can swim under and open your eyes, but I wouldn't dare do that now.
The river right now is trying to transport all the sediment that's coming off of the large landmass that was burned by the High Park fire. You got all this 80,000, 90,000 acres of drainage area that comes to the Poudre. All of that sediment has to come off of that terrestrial stuff and end up going into the Poudre, and the Poudre have to actually transport it downriver to get it out of the system.
Because of the fire, we have more debris in the river, so we just are keeping a mindful eye on what's downstream rather than relying on memory. It's also a little bit harder to see rocks because the water's dark. I think that people should experience this because it's like a 30-year event, and we're probably not going to see a forest fire in this region for a long time, so it's kind of a cool, to see what nature can do. the river's running black, you're probably not going to ever experience that again.
Yeah.
Well, I don't think I will.
It's a once in a lifetime thing for people to experience. I mean,
So-
you're never going to say you got to raft a Black River ever again.
Yeah.
So.
What happens with the fish is the fish has to survive all this sediment and silt that's coming down the river, and what happens is it seems to clog their gills and provides them issues with trying to breathe while they're in the river. And then long term is all this sediment and silt coming down will fill in all the spaces around the rocks and cobble in the river where the aquatic invertebrates or the bugs live that is the food source for those trout. And so we'll lose your classes of invertebrates in the river as well.
There's going to be a cycle to this. It's okay, it's part of the process. And we thought it was important for us to see and to show our kids when we came up here that, yeah, the destruction was amazing, is overwhelming, and there's already green things growing back through the charged soil.
Every day you come up here, it may look the same, but it's different water that you're looking at. It's just a dynamic system.
Yep, that's great. Great, thanks, Brian. So what do you think? In looking at that water in that video, do you think wildfires could lead to turbidity levels that exceed 10 to 100 NTU? Probably. So what we have on the left is that 100 NTU, so that's the maximum a water system could really handle. And so from a study that took different grab samples along that river post-fire, they found turbidity levels exceeding regularly 800 NTU. So that looks like that totally opaque sample on the right. Right, so a water system really is no match for that level of particle load in such a high turbidity. And so because of that, the Fort Collins water system that relied on that water source as their primary water source had to find an alternative supply, which they fortunately did have as a backup for about 100 days. But there aren't, not all water systems are as fortunate as the city of Fort Collins and have a secondary supply. So you can imagine what that might do to a city kind of in terms of day-to-day life. If you had to shut off your water for 100 days, it'd be pretty devastating. And what's particularly concerning for the Pacific Northwest is that we're not really accustomed to dealing with high levels of particles and high turbidity levels. Fort Collins, they often have to treat under normal conditions high levels of particles. And so because of that, they already had a conventional water treatment plant, right, that can handle turbidities that fluctuate all the way up to 100. Through some of our analysis of water systems throughout Oregon and Washington, we actually see that less than 80% of water systems in Oregon are conventional. So about 19% are conventional. Sorry, I misspoke there. So about 19% are conventional, and in Washington, it's less than 10% are conventional. So in other words, about 90% of our water systems in Washington state are direct filtration facilities. That means they can handle a maximum of 10 NTU. But what could be coming down the pipe if we have major wildfires, like they saw in Colorado, that lead to elevated turbidities, you're looking at an 80-fold gap between what a water system is designed to treat, a typical water system is designed to treat in Washington, and what a wildfire could actually do. So again, just want to highlight, we have most of our surface water treatment plants in Washington state are designed for about 10 NTU. Okay, so one of the first aspects of this project that began about 2 years ago is starting to try to profile what are the problems that water systems in Oregon and Washington are facing, and how successful are they dealing with these problems. So the first kind of case study that we looked at was in the McKenzie River watershed. And that McKenzie River is the primary and actually sole water source for the city of Eugene's water supply. And so Eugene is kind of down in that bottom kind of left corner where you see that red star. That's where the city of Eugene's intake is for their water treatment plant. And so the Holiday Farm fire in 2020 burned about 18% of the watershed. So it's kind of that brown-orange area within the watershed boundaries. And so the watershed boundary is shown by those blue lines. And much of the burn area was of a pretty decent severity, so about 66% of it was moderate, and we'll look at some pictures later of what a moderate severity versus a high or low severity burn looks like. So definitely the water systems, including Eugene, but others that rely on the McKenzie, were quite concerned after this Holiday Farm fire. And so the Eugene Water and Electric Board Water Treatment Plant, or acronym is EWEB, they are a conventional water treatment plant, fortunately. And so you can see kind of that red line in the middle is when the Holiday Farm fire occurred. To the left of that is what the turbidity looked like before and what the turbidity did after. You do see one major spike before the fire in turbidity, which is associated with a really big storm event. And so these spikes that you see along the way are all associated with kind of these major storm events that cause some flooding and erosion. In general, what you can see, though, is that post the Holiday Farm fire, there's a lot more peaks that are much higher than pre-fire, with that one outlier kind of between 2018 and 2019. Fortunately, what we saw, though, is that the conventional water treatment plant was able to handle the turbidity well. So in the top plot, we're looking at the finished water turbidity, so that's what exited their water treatment plant. What the bottom plot is their raw water turbidity. And so the vast majority of the time they are able to not exceed their 95% threshold, and only here and there exceeded it, but could always stay below the 100% threshold. And so while this is largely a success story that post-wildfire, so long as your turbidity doesn't remain elevated above 100 NTU, if you have a conventional facility with a sedimentation basin, you should be able to weather this wildfire storm. That said, though, there are still additional costs that get incurred, even if it doesn't cause your water treatment plant to fail. So it's a little bit hard to see due to the scale, but on average, the turbidity post-fire was 1.5 to 2 times larger than it was pre-fire. So the turbidity kind of came up and then flatlined. It never really dropped very low again. This is problematic just because one of the main costs for a water system in terms of their continuous operational costs is disposing of the solids that they either settle out or that get filtered out. And so we know from different kind of empirical studies that as turbidity increases, you see that the mass of the solids that need to dispose simultaneously increase. So if you're looking at doubling your turbidity, you're looking at basically doubling your solids disposal costs, which is often kind of in the top 2 or 3 of operational costs for a water system. And that cost ultimately gets borne by the communities that have to pay their water utility bills, but then have to pay more for the water treatment plant to dispose of these contaminants. Okay, so now let's come over to our objective 1B at a water system, and that's to address contaminants causing chronic disease. So that's primarily dissolved contaminants, so not particles. Conventional treatment is largely ineffective here, wildfire or not. And actually, the disinfection that's required by law to provide to make sure we're complying with Objective 1A is actually detrimental to dissolved contaminants. And the reason why is because it actually forms contaminants. So we're going to be seeing these two acronyms a lot. So one of them is DOM, that stands for dissolved organic matter, and the other is DBPs, which stands for disinfection byproducts. So when you have dissolved organic matter present, or DOM, when you're disinfecting the water, which again, you're required by law to do, you can't send non-disinfected water out to people's homes, that chlorine will react with the DOM and is a byproduct of disinfection. So it's unintentional. You want the chlorine to kill the pathogen. You don't want it to react with the DOM. You get these disinfection byproducts. It's an unintended byproduct of disinfection. And we know that wildfires will release pyrogenic DOM, so it's kind of that black charred material. It'll ultimately dissolve into water, and what its influence is on disinfection byproduct formation is not fully understood, and so that's something that we've been starting to research. Okay, so I want to do a little bit of an overview of what dissolved organic matter is, because we're going to be talking about it so much. So imagine you have this stream with lots of healthy vegetation. So there's a stream kind of running down the middle of that photo with lots of vegetation surrounding it. Ultimately, what will happen is some of that vegetation will die, and then you'll have soil organic matter on the ground. So if you were to kind of zoom in there, you would see soil that looks like that with lots of organic material. Eventually, when you have a rain event, it will mobilize some of the compounds that can dissolve into water. So if you were to kind of zoom in on that water, you would see these large molecules that look like this. So this is kind of a typical dissolved organic matter kind of hypothetical compound. If you were to also zoom into the stream, what you might see is little aquatic organisms like algae. And when those organisms die, they release things like proteins, maybe DNA. When those molecules then move through the stream, they interact with sunlight, they interact with other microorganisms that eat these molecules as food. And then you ultimately get a mixture of compounds that might kind of look like this. So for those of you who haven't taken organic chemistry in a while, wherever you see, and these kind of, you'll be seeing these molecule structures a little bit. Wherever you see a little node, like I'm gonna walk outside of the camera for a second, but wherever you see a little node here where there's nothing drawn, just a bond, there's a carbon element there. So you can see lots of nodes with no element. So these are enriched compounds with lots of carbon. So that's what makes them organic compounds. They just have lots of carbon elements in them. And so what I want to highlight is that DOM, it's a mixture of organic carbon-containing compounds. It's not one type of compound, it's probably millions of different types. And if you have a lot of it in your water, it'll kind of turn the water yellow. So that picture right there is water containing lots of dissolved organic matter. Okay, so now let's talk a little bit more about what disinfection byproducts are. So if you add chlorine to water that has dissolved organic matter, that chlorine will react with the DOM and will continue to react more and more with it. So we're kind of looking at a DOM molecule, and one chlorine element attaches to it, then two, then three. And ultimately what will happen is you'll get contaminants to kind of break off. And so what we're looking at there is the compound chloroform. And so some of you may have heard of chloroform before. It's a, anthropogenic compound that, will make for different industrial purposes maybe. It's also used to maybe knock people out, but it's actually something we intentionally form in our drinking water. There's 4 different types of trihalomethanes. Chloroform is one of them, and they're regulated at the federal level by the US EPA at 80 micrograms per liter. So you can't exceed that level in our drinking water or you'll get a water quality violation. There's another important class of disinfection byproducts called HAAs, and this is an example of an HAA. Okay, so this might seem kind of like esoteric, like a interesting thing to study in the lab that's like kind of this random, unintended reaction. But it's actually maybe the most important class of contaminants in our drinking water in the US, because DBPs are the leading cause of health-based drinking water regulation violations in the US. Some years there might be some other ones that take that first spot, but it's usually disinfection byproducts. In Spokane, we have fortunately pretty low levels of dissolved organic matter in our water, and so because of that, we don't get a lot of disinfection byproducts in our water. But if you look kind of at the bottom of this table, this is taken from the Consumer Confidence Report that the city of Spokane publishes every year. And so in 2024, you could see THMs, so primarily chloroform, was present at about 4 micrograms or 3 micrograms per liter in our water, which is less than the regulated limit, right, of 80 micrograms per liter. So that's why you weren't notified about it in the mail that you were drinking chloroform from time to time. But if you were to open up our taps, you would be able to detect chloroform in that water. Okay, so some of you might then be thinking, okay, so we got to chlorinate our water. It reacts with DOM and forms the DBPs. Well, why don't we just not chlorinate the water? Maybe do something else. Well, it's required by the US EPA. It's kind of cut off at the bottom, but we need to have detectable chlorine in all of our water, including coming right out of our faucets. So if our chlorine isn't above about 0.2 milligrams per liter in our water, that water is deemed non-compliant with federal regulations. And so because of that, we have chlorine moving through our whole system with lots of time, sometimes days, to react with DOM. We get lots of disinfection byproducts that form through the system. And so this is maybe the biggest challenge of water treatment professionals, arguably, is that you need to both provide disinfection, make sure there's adequate levels of it, but simultaneously not form too many disinfection byproducts. Okay, so now let's come back to thinking about upstream in our watershed, but now we're looking at having a fire. If we were to look at that burned stream now and look at the soil, it might look charred like it does here. And then as rain would pass through that soil, we would see a different distribution of organic compounds get released. And so we would call these pyrogenic compounds. So there may be smaller, there's these fused rings all together, and they generally have fewer oxygens in them. Likewise, if we have less vegetation covering our stream because of that fire, we'd expect there to be more algal growth. And with more algal growth, we'd get more of these kind of biomolecules, more proteins, more DNA, things like that in our water. And so this is maybe what the profile of our water would look like post-wildfire. We'd have these pyrogenic DOM compounds and some more kind of microbial-derived organic compounds. So the question that we wanted to answer, part of this research project we started a couple years ago, is how do wildfires influence the formation of disinfection byproducts? So if we have a different type of pyrogenic DOM compound reacting with chlorine, what are we going to get? We also want to think about what is the role of DOM concentration. So are wildfires going to maybe change the concentration? And what is the role of the character or the quality of DOM in forming disinfection byproducts? Okay, so pop quiz. So which sample will form more DBPs, sample A or sample B? I'm seeing some Bs out there. That's good intuition, because in sample B, we have more compounds, right? So we have more of these DOM compounds. We should form more disinfection byproducts. The way we usually measure the amount of DOM is using something called dissolved organic carbon, where we just measure all the individual carbon elements. So after wildfire, will water become more like sample A or more like sample B? So this is at least one meta-analysis. So it surveyed 14 different studies that looked at 38 different sites between those 14 studies. In kind of this early time period, which was between years 1 and 2, they actually saw that the response ratio, so just the amount of DOM or DOC post-fire relative to unburned sites, they saw that ratio increase. So suggesting maybe, by a factor of 1.2 or 1.3 on average, you'd expect that level of increase in the DOC. So this kind of meta-analysis suggests B, that post-fire we'd expect to have more dissolved organic matter. More dissolved organic matter means more DBPs. Okay, another pop quiz. So which sample will form more DBPs? Now if you look at sample A and B. So there's the same number of carbons here. Each one of those molecules has 6 carbons, so the concentration is basically the same. So there'd be no way, I think, to guess this. unless you've read a bunch of papers about it. And it would actually be sample A. So that compound with those oxygens on it is highly likely to form lots of DBPs. And actually, for every milligram of dissolved organic carbon you have that compound on the left, you would actually get 1.5 milligrams or 15,000 micrograms of DBPs that form, whereas the compound on the right won't form any if it reacts with chlorine. In the Spokane River, for instance, we have about 1 milligram per liter of dissolved organic carbon on average, maybe a little bit more in the river. And so if you had 1 milligram per liter of that compound on the left, you would get something that is at 1,500 micrograms per liter, or more than an order of magnitude higher than what's the safe level. Okay, so finally getting to the study design here. So we collected samples, or I did, and our collaborators out in Oregon went to these 2 different burned sites. So in the McKenzie watershed and the Salmon Creek watersheds. They collected samples from these different catchments where they would characterize the catchment based off how much of it had burned, at what severity. And a catchment is just anywhere where any rain that falls in that area won't leave that boundary and will ultimately enter into a river or a stream. So this first site we looked at, and this work was primarily done before I got involved with this project, but I think it's helpful to kind of see what was the effect of fire in the Pacific Northwest on DOC concentrations. So they sampled all these different sites where you see those circles, or those diamonds, and then kind of upstream and downstream of the fire to see how is the fire impacting DOC concentrations. They did this in over 3 different storm events, and then they had an additional sampling campaign in the summer during a dry month. What they saw was somewhat unexpected in that the burn severity across the 4 seasons was actually negatively correlated with burn severity. So that top bar there shows that there was, again, a negative correlation. With more burning, you would actually have less dissolved organic carbon. And so kind of the key takeaways from the studies that suggest that, at least in the Western Cascade watersheds, that more burning may actually cause a decline in the amount of DOC. But the caveat to that is that this was only done kind of 2 years post-fire. So this suggests maybe the long-term effects of fire might not be that problematic, at least in the Western Cascades. There's kind of unique hydrology in the Western Cascades that's like different from places in Colorado where we were watching that video. And that in Colorado, when you have a rain event, most of that water remains on the surface and will be surface runoff. And so it will mobilize and suspend all of the contaminants and then mobilize them into a stream. What's more often occurring in the Western Cascades is that water will infiltrate into the subsurface and then move laterally below the subsurface and then re-emerge into streams. So we have more of that lateral subsurface flow. That's kind of why it's hypothesized that we're probably getting some natural treatment from the water moving into the subsurface, resulting in less DOC in our streams post-fire. Okay, and so this is a study that I led starting about 1.5 years, 2 years ago. Did I do something? So similar to that last study, we had these 4 different sampling campaigns where we sampled anywhere from 30 to almost 60 samples across this burned watershed called the Salmon Creek watershed. We took these samples, filtered them to kind of stabilize them, and then added high levels of chlorine into these samples, held for 7 days in the dark so that we'd form DBPs, and we made sure we had about 3 to 5 milligrams per liter of chlorine remaining. So this was just kind of to maximize the amount of DBPs that could form. So this is called a DBP formation study. And then Eric Ross in chemistry here at Gonzaga measured on a GCMS the HA9s in THMs. And so interestingly, what we saw here is that in the winter season, which was closest to the fire, is that it decreased the amount of DBPs per milligram of DOC, at least for HAAs. We didn't see much of an effect in the spring and summer, maybe a small effect in the fall. That was still statistically significant. So the key takeaways that the proportion of the catchment burned negatively correlated with HA9 yields in the winter and fall. And this would suggest that if we had 100% of our catchment or watershed burned, this would actually decrease yields by greater than 50%. On THMs, there was no statistically significant effect. But then when we looked at the different proportions burned at low, moderate, and high burn severity, we saw that moderate burn severity, so the more moderate burning we had, that would actually lower the amount of THMs we would form. Where the effect was not statistically significant on HAA9s. And here's just a picture of kind of what low, moderate, and high burn severity looks like. So low, you still have some greenery. High burn severity, lots of trees falling over. Moderate, you still have some trees remaining, but they're pretty charred looking. Okay, so the summary of these results is that 1 to 2 years post-fire, DBPs may actually decline because we have a decreased concentration. So pre-fire, we generally have higher DOM than post-fire, at least in the watersheds where the study was done. We also might modify the character, which was what we were looking on the last slides, where we saw lower DBP yields, so less DBPs per milligram of DOC. So we think pyrogenic DOM is actually less prone to form disinfection byproducts, which is good news overall. So the future work is that we want to study DBPs in samples collected more recent to fires, and then try to examine other regions like the Eastern Cascades, which we think might be more similar to like the Rockies, where they've seen more problematic issues associated with DOC post-wildfire. The implications for this is that prescribed fire, so particularly if we targeted a moderate severity, which most prescribed burning tries to achieve, or maybe low severity, that could benefit drinking water quality. So prescribed fires might reduce risks of megafires, but also temporarily improve water quality downstream. Okay, so these next slides I'll go through pretty quick. They're a little shorter. So another type of contaminant that we're concerned about with the wildfire are cyanotoxins. And cyanotoxins are dissolved contaminants. Conventional treatment not going to be effective against them. So why would we expect more cyanotoxins? And what are cyanotoxins? So cyanotoxins are derived from harmful algal blooms. So post-fire, you'll get more nutrients, so things like nitrogen and phosphorus, that will get mobilized. They'll maybe enter into the atmosphere and then get deposited into water bodies. So the more nutrients you have, the more plant life can grow, so algae primarily. And if you were to zoom in to a harmful algal bloom, what you would see is things like this compound called cylindrospermopsin, which is a cyanotoxin. Other cyanotoxins can be neurotoxins, so they'll damage the brain. Cylindrospermopsin harms livers and kidneys, and it has kind of a health advisory level of about 10 micrograms per liter or so. Actually, it's 3 micrograms per liter. Okay, so we know that we're likely going to have more of these cyanotoxins post-wildfire in our water. The best available technology to control cyanotoxins like cylindrospermopsin or CYN is activated carbon. So it's the best available technology. It's applied at a large scale at municipal water treatment plants, but many of you have used activated carbon without knowing it, like in a Brita filter. So many point-of-use home filters use activated carbon. If you were to zoom in and look at what that activated carbon looks like, it's this highly porous material. And such porous material like activated carbon just has lots of areas for contaminants to come and stick. So basically, it removes contaminants by attaching the contaminant to its surface. So if we had pure water, so nothing else in it, if we maybe wanted to get an order of magnitude reduction in CYN, so get 90% removal, some of our lab work showed that we would only need to add about 1 milligram of PAC per liter. So that's not very much to get a lot of the contaminant removed. However, when you don't have a pure water sample and dissolved organic matter is present, we saw, for instance, with one sample, we needed to add 6 times as much of the PAC, so about 6.5 milligrams per liter to achieve that 90% reduction, so that we only had 10% remaining. The reason why that happens is if you have a DOM compound, it will come and stick to the surface of your powdered activated carbon. and then it will block or basically compete for the adsorption site, so the contaminant can't stick and absorb to the surface of the PAC. So then the question that we wanted to ask is, how does the presence of pyrogenic DOM impact the ability of PAC to remove cylindrospermopsin? So is the pyrogenic DOM going to win out and stick to the PAC, or will the CYN? So in this study, we use these ISCO samplers. So it's basically an automatic sampler that you put it into the field, and you can set it for different times to take a sample. So in this study, it was every 2 to 3 hours it would take a sample. And we set those up at these burned sites in this fire area from the Lane 1 fire that occurred a little bit south of Eugene, Oregon. And then we had these reference sites that were unburned. Here's an example of a hydrograph showing kind of the flows during the sampling by the ISCO samplers. So there was this kind of initial storm here, and then kind of a second more intense or storm that occurred a little bit later. Okay, so what we're looking at on this plot is the dose needed to remove 90% of the CYN. So we basically took what we looked at on that previous slide and then plotted that on the y-axis. So basically we don't want to have to move further up the y-axis, because the further up we move, that means we have to add more and more of our PAC to achieve the same level of treatment of 90% removal. So that's what it looks like in the burned watershed. And so kind of that rising and falling is associated with having more contaminants mobilized from the storm in that burned watershed. So before the storm, we only had to add 4 milligrams per liter, and then at the peak of the storm, we had to add about 9 milligrams per liter. In our unburned watershed, we saw much less sensitivity to storms, and overall, we needed to add a lot less PAC in the unburned watershed. And so on average, we had to add basically about twice as much, double the amount of PAC to remove the same amount of this contaminant, CYN. When we plot the DOC, so that's what's shown kind of by those brown lines, we actually had higher DOC mobilized in the unburned watershed. So what this suggests is that the burned watershed wasn't bad for the PAC because there was a lot more dissolved organic carbon post-fire. It was because the quality of the pyrogenic DOM, so the DOM from the burned system, was much more competitive and really harmful to the PAC performance. So to summarize these results, the DOM influenced by fire could challenge the ability of water treatment plants to remove harmful organic contaminants like cylindrospermopsin. So the implications, water treatment plants may need to prepare to add a lot more PAC to ensure safety post-fire. Okay, and then we're almost to the finish line. So the last objective is, the second objective is to provide aesthetically acceptable water. We know that post-fire, you can often smell smoky odors, and those smoky odors will remain in the water and often penetrate through a water treatment plant, because water treatment plants aren't designed to remove these odorous compounds. So the Eugene Water and Electric Board, which again is this conventional water treatment plant, and we're looking at its process flow diagram that treats all water for the residents of Eugene, Oregon. They apply PAC primarily to control taste and odor. If you look at the Eugene number, so the number of complaints that were registered to the Eugene water treatment plant, so this is basically residents calling in and saying, you know, my water looks bad, it tastes bad, it smells funny. Pre-fire, the frequency was much less than post-fire. So a lot of these complaints were associated with the water looking dirty. So we know that the wildfire, it was making the water look aesthetically unacceptable, so people didn't feel safe drinking it. That's really important to water treatment plants. They want to maintain trust in the community. So this suggests the Holiday Farm fire mobilized color compounds that made the water look dirty. And then you can also see the amount of times they had to pretty much apply PAC following the fire was like 5-6 times as much as pre-fire. So this again suggests that the fire required more PAC to be added, which they add primarily to control taste and odor compounds. So this suggests that lots of taste and odor compounds were kind of making it into the water treatment plant. They were getting more complaints, so they started needing to add more PAC. Okay, so summary of the presentation. Wildfires pose risks to drinking water safety and water treatment plant operations. Wildfires, though, can actually improve water quality. In the case of the disinfection byproducts, at least in the Pacific Northwest, on the Western Cascades, that's the case. Might not be the case everywhere, so that's kind of future steps is to figure out under what conditions can wildfires actually limit DBP formation. But we also saw that it could harm water quality by making it really difficult to remove potential neurotoxins, compounds that target livers and kidneys like cylindrospermopsin. Didn't have time to kind of touch on this, but the work on this project is a transdisciplinary study between myself, others at MSU and Oregon State that are environmental engineers, but we're working with watershed modelers, watershed kind of samplers that know how to kind of instrument a watershed. And then we're also working with economists to kind of quantify the economic impacts of wildfire on our water. Future work is that we want to characterize the impact of wildfire in distinct Pacific Northwest watersheds. So we're starting a study at the end of this fall semester in the Eastern Cascades. And then we want to start identifying smoky compounds that reach water systems post-fire. So we're not exactly sure what these compounds are that are making the water look, smell, and taste bad. To do that, we got this cool instrument called a GC olfactometer. I think I said that right. That our analytical chemist, Eric Ross, is going to be using to smell lots of smoky odors. And basically, he'll smell the sample, press a button if he smells a compound, and then the instrument will then identify what that compound was that caused that odor. Just want to thank a lot of the number of the people that were involved in this research. So Dr. Eric Ross did kind of all of the analysis on the disinfection byproducts. Kevin Bladen's group is leading this overall effort on this wildfire and water security grant that was funded by the U.S. Forest Service. He's at Oregon State. And then I have my main collaborator at Montana State, Dr. Amanda Honer. And then Ryan Cole did kind of all of the field sampling here. And then this is just a subset of the undergraduates who have been involved with this research. There's been many others here at Gonzaga that have been involved with this, but these are the ones that primarily contributed to the research we discussed here. All right, and with that, I can take any questions if we have time.
Excellent. Thank Dr. Shimabuku. So start thinking of your questions, and I'll start with students first. But I was hoping to go back to something that I think I understood you saying at the beginning about conventional treatment and sedimentation. Were you saying that in the West, we don't typically have a lot of facilities that are using conventional treatment for sedimentation, and so when we have a wildfire, it creates a lot of sediment. We don't necessarily have systems that are capable of handling that. Can you go back to that part? Because that seems like, you know, from my perspective, bearing the lead a tad, just because, or maybe there's the part I'm most interested in. How many facilities are on the West, are just sort of not going to be prepared to be able to handle high, sediment events? Yeah. So did I track that correctly?
Yeah, you nailed it, Brian. Nice work. So yeah, because, and we see it more so in Washington, where we have much fewer systems with sedimentation basins. So it's less than 10% that are conventional. So 90% or more are direct filtration. They have no sedimentation. The reason why that's the case is because our water in general is really clean in Washington. It's cleaner than it typically is in Oregon and cleaner than it is in California. And so because of that, it puts us at a greater risk of dealing with a big spike in contamination because our water systems just aren't used to it.
So we have a couple different factors. We have better water usually. We might have lots of fires where we don't have systems that are designed to be able to handle those types of events. But we also have hydrology that may function differently the way that the water run, if it infiltrates and filters a little bit. I think of the geology around here, that seems to be a lot of the case. So it sounds like a mixed bag a little bit in terms of the effects that it would have then, right? Because it's not all gonna, sounds like it's not all gonna run off as much as it does in Colorado.
Exactly, because there's less overland flow, essentially. There is some kind of built-in natural resilience in our watersheds, but that's true at least in these sites we've been studying as of late. It could be a different story, and we suspect it will be kind of on the eastern Cascades. So a place like, Wenatchee, that relies on surface water, they don't kind of have these soils that want to infiltrate water quite as much.
Excellent. Any questions for Dr. Shimabuku from the audience? Who's got a question? Maybe mention your name if you're willing.
Yeah, my name's Bob Merrill, and I'm a retired water system operator. And my question is as an operator, you're always concerned about the chemistry of the water coming into your plant. And I'm talking about charges and stuff. The plant that we operated in Linden during the rainy season, there was a lot of organics in the water. And then in the summer, you got a lot of flow coming off the glaciers, and so that's mineral, and you treat them differently. Did you notice any changes as far as treatability, as far as that goes, like water chemistry and how it affected how the plants operated?
Thanks for the question. At least on the types of treatment processes that I'm primarily looking at, so looking at like activated carbon, some of that kind of inorganic chemistry, so kind of the charge in pH, that type of process is a little less sensitive to. But my colleague and collaborator at Montana State who studies coagulation, it's very sensitive to kind of the pH, like buffering capacity, things like that. And so I was just kind of looking at the results a little bit from this Lane 1 fire where I shared some results, and she saw that the coagulation really struggled post-fire, and it probably has to do more with some of those things you talked about, not so much like the DOM that I was talking about, but more kind of the inorganic nature of the water, so like what's the pH, what's the buffering capacity, things like that. So yeah, definitely a challenge that's kind of invisible to many water treatment plants.
You talk at the end about prescribed burns, and I was thinking about mega fires in particular. You talk about low intensity and high intensity. Are mega fires sometimes having even? I'm wondering if you were actually eliminating a lot of the standing trees. Would I be right in assuming that those extremely high burns would then have even more of this pronounced effect since we're experiencing those really, really intense events?
Yeah, that's right. So the more severe a wildfire gets, you would expect worse outcomes. A big part of that is because you have less vegetation standing to kind of prevent major erosion and flooding events. You also will find more often that the burned materials have more water repellency. So at a high burn severity, you basically have material that gets deposited that really likes to repel water, so it keeps the water at the surface and flowing over. Right. So high burn severity, you would expect in general worse outcomes. That said, if you really burn wood all the way down to ash, what you're left with is just ash, which is inorganic compounds, and you don't have a lot of the organics, which is really arguably one of the biggest issues at a water treatment plant. So there's always kind of a benefit and a trade-off to a lot of these things.
Interesting. Thank you. Yes, let's go to the middle here.
My name's Linda Carroll. I'm wondering if there's any hope for a compound that would kill pathogens that's not chlorine, that would be less prone to create other harmful compounds. I mean, I'm thinking in terms of my washing machine, we use hydrogen peroxide bleach instead of chlorine, but I don't know if some other kind of compound like that could be used.
So there are other disinfectants that can be used. For instance, UV light can be used, or ozone can be used, but Those really can only be used as primary disinfectants, it's called. So you can kind of see coming out of your water treatment plant, I have this disinfection basin shown. That's where you can apply those, is at the facility. But you don't want to send ozone into your drinking water for people to drink. And you also can't really feasibly line a whole pipe network with UV light. So at least as a secondary disinfectant, because, and I don't know if I have the distribution system kind of pop up here, I don't, but we need to make sure we have a disinfectant moving through the whole distribution system. So because of that, chlorine is really kind of our best option. So we can combine it with other disinfectants that can lower disinfection byproducts to some degree, but we're mostly stuck with chlorine. The alternative is something called chloramines, where you basically combine chlorine, and by chlorine, really what we're talking about is household bleach. So the active compound in bleach is what all of us drink every day. If you combine bleach with ammonia, you get chloroforms, and that forms fewer disinfection byproducts, but the ones that form, like this compound NDMA, which is rocket fuel. So those of you that have lived in the Southwest, where we have a lot more chloroform used, have consumed rocket fuel from time to time. That compound, it's unregulated, but we know it's more hazardous. So there's a bit of a trade-off there. So there's other approaches, like for instance, in Europe, they just add less chlorine or not at all in some places, so they don't get the DBPs, but then there's a bit of a trade-off with potential recontamination with pathogens.
Like the name of an energy drink, right? Sort of. Maybe one last question. Yes, sir.
Hello. I used to work for the city of Walla Walla, which has a very huge watershed area. I think it's 36 square miles, and it's at fire risk. Ironically, the reason why there's a higher fire risk because we put out fires very quickly. So the intensity of the forest is bigger, and it's older. And we're wondering, okay, what's the trade-off? Should we be doing more prescribed burns? In Washington area, we use more piles versus broadcasts. But is there a balance that we could do and maybe take those culled trees and create more of a mulch that would filter things out?
So yeah, really great questions, and good to see you again. I'm certainly, try to stay in my lane and speak to what we can do at a water treatment plant. I know a lot less about land management, but we're working on this interdisciplinary project, and so when I've talked to the land managers on the project about our results, they were excited to hear that these moderate or low intensity burns seem to benefit water quality. And so if you do a prescribed burn, that's kind of what you're trying to do. So it seems like that, at least preliminarily from our data, seems like that would be a good route to go to reduce megafires and also provide at least some water quality benefit with respect to one class of DBPs. With respect to the using like mulches and things like that to kind of as a remediation procedure, kind of post-fire to get things to reestablish. The little bit of work that I've seen on that we might try to follow up on is, depending on the type of mulch, you could really have maybe a benefit to water quality or really diminish it. So like straw mulches leach a ton of organic matter. So if you use straw, you're probably really gonna degrade your water quality. But wood mulches can help actually retain particles, so then you would benefit kind of that turbidity issue. So yeah, thanks for your question.
I know that you said you wanted to stay in your lane, but I'm interested, have you had any challenges with the funding from your federal agency for this work?
We've been pretty fortunate so far, and I think it's because the title of our project is water security, so I think that security word in there really helped us out.
Well done,
yeah.
Well done. Very, very, very smart. Well, let's thank Dr. Shimabuku. It's really exciting to see my colleagues in engineering doing this really important work with students and from our chemistry faculty as well. It's a great interdisciplinary collaboration both here at Gonzaga and then with some other colleagues at other universities. Don't forget that we have an event on December 2nd on environmental justice in Cancer Alley on Zoom. Hope to see you there and have a great lecture series next semester. Thanks. See you next time.